Welcome in. My name is Jason Ostanek. Today we'll talk about the del operator. The del operator is like any other mathematical operator. It's waiting for something to operate on. The symbol we use is this upside down triangle. And the del operator, you'll notice it looks like a vector. It's got a unit vector, I, j, k, multiplied by a partial derivative in x, y, and z. Now, the result of your del operator depends on which operation you're performing. And there are four vector operations which use the del operator: gradient, divergence, curl, and Laplacian. Let's start with gradient. To compute the gradient, you feed the del operator a scalar field. So I can see right here I've got my del operator and some scalar field phi. And the result of that is my unit vector I multiplied by the partial of phi with respect to x plus unit vector j partial y partial phi partial y, excuse me, plus unit vector k partial phi partial z. So the result is a vector. We can do a quick example. If we've got some function phi that depends on x and y, so there's no z dependence here, we can calculate the gradient at a value of x1 and y1. So the first thing that I need to do is calculate the partial derivatives of this function with respect to all of its independent variables. So the partial phi with respect to x is 2x, which I can see right here. So I wrote the gradient of phi and I broke it out into its individual components, still in function form. I haven't calculated any values yet. So in the x direction, the partial of phi with respect to x is 2x. And the partial of phi with respect to y is 2y. So if we evaluate this at 1, 1, our gradient value is 2, 2. So what I'm going to do is open another interactive tool. You may see this in the other videos where we can try out the gradient operation. And what's important to recognize is the gradient measures how steep the function is, and the direction of the vector points uphill. I'm going to illustrate that. Let me pull up the tool. Okay, I've got the vector operations tool open. I've zoomed in. I'm in dark mode, so hopefully it's easy to see. And what I'm going to start with is a scalar field, of course. Since we're talking about the gradient, we feed the del operator a scalar field. So let's use this function here, x squared minus y squared. And what we're looking at currently in our contour plot is the field itself. So I've got phi selected. Okay. So I'm looking at the scalar and I haven't done any operation on it yet. We're looking at the function as it is. And what I want to do next is click on the gradient operator here. So that's del symbol feeding it a value of phi. And what you'll notice is that we're no longer looking at our function, but we're looking at the gradient. And I know that we're feeding a scalar into the del operator and we get a vector in return when we take the gradient. And I mentioned before just a moment ago that the vector field that we get tells us how steep the slope is, and the arrows are always pointing uphill. So let's see if that's true. If I go back to my function here, I can imagine this as hills and valleys. And the red contours are hills, they've got positive values. The gray is near 0, and the blue is valleys. So I've got these ridges here, the gray values kind of making an X formation. And I've got two hills and two valleys. And now let's take a look at the gradient. And sure enough, my arrows are pointing uphill. I'd walk up the hill going from the center out to the left here, and I'd walk up the hill this way. Now, if I go back to the field, we've got these valleys here. So to walk uphill, I would need to go up in y, and then from this position, I would go down in y. Let's see if that holds true. Yep, my vectors are pointing inwards, so I'm walking uphill. And the magnitude tells us how steep the hill is. Kind of right here at the center of the graph, my hill's not very steep. I'm at this intersection where I've got practically no hills nor valleys. So in fact, the dot represents a point where the vector is exactly 0. Okay, so go ahead and try out some different fields, scalar fields, and take a look at the gradient and see if you can understand what your field looks like, and maybe take a guess before you click the gradient of what your gradient vector field would look like. In this case, it seems like they're all going to be pointing outwards, and they sure are. I'm walking uphill in every direction, and the steepness of the hill gets steeper and steeper the farther I go out. The next vector operation to cover with our del operator is called the divergence. To compute the divergence, take the dot product of del and the vector field. So I've expanded del out here, and the vector field f I've expanded out. And again, just like we did with dot product, we can dot each term with one another. So my unit vector I and partial with respect to x is going to be dotted into each of the 3 components of the f vector. Same thing with j partial with respect to y and k partial with respect to z. And if you recall from the dot product, when we dot unit vectors together and we represent all the combinations in this 3x3 matrix, we get the identity matrix. So the only surviving terms are when we dot a unit vector with itself. So I've now carried the dot product out through each term. So I've got I dot I right here. And now I'm taking the partial with respect to x of a scalar f1. So that f1 just goes into the partial. And then I dot j partial f2 with respect to x, and so on through all of the different combinations. And again, the surviving terms are going to be I dot I, j dot j, k dot k. And these dot products become scalar values of 1. So the result and the formula that you need to remember for divergence is the partial of each component of the vector field with respect to that component's direction. Take the partial of each component in its respective direction and sum together. And the result is a scalar field. Let's do a quick example. I've got vector f, which depends on x and y. Its components are x squared, y squared. So taking the partial with respect to x, 2x, plus the partial of f2 with respect to y is 2y, evaluated at x1, y1 gives me 4. Let's go ahead and open the interactive tool and try out the divergence. Okay, we're back in our vector operations tool. Now we're going to feed our del operator a vector field. Let's just first take a look at our vector field here. Our x component is equal to x. So as we go farther in positive x direction, our x component is growing. I can see that by the size of the arrows. And if I go left, my x component is now negative x, and it grows in magnitude. Same thing in y. Okay, so that's our vector field we're going to start with. Now let's go ahead and take the divergence of this field. And I notice that it's 2 everywhere. So let's go ahead and think about this. If we take the partial of f1 with respect to x, I get 1. and the partial of f2 with respect to y, I get a value of 1. I can see that by inspection of our two vector components. And adding those together, I get 2 everywhere. Let's take a look at another function here. Let's try this one. So now I've got f1 is y, f2 is 0. So my vector field, it has no y component. And its x component depends on x. I'm sorry, x component depends on y. So as we go up in y, our x component gets stronger. I can see that by these size of these vectors. Now, before we click on the divergence operator, let's see what we're going to get. If we take the partial of f1 with respect to x, this is treated as a constant, so it becomes 0. And the partial of f2 with respect to y also becomes 0. I'm expecting my divergence to be 0 everywhere, and it is. If you have a flat gray everywhere, you've got a divergence of 0. Okay. Now, the divergence, what it measures, it really tells you the net outflow. So if you look at your vector field, the way I think the easiest way to think about it is, if you think about this vector field in 2 dimensions, does it seem like you have a source or a sink of flow? If you think of these as like a velocity field, like a flow field, where is the source coming from? Well, it seems like our flow is kind of coming in plane. Down here, like the flow is going right to left. So the source is really in plane moving right to left, and up here, kind of the same thing. Now, if I go back to this one, it's actually labeled as source. It certainly looks like this flow field has some source, like it's like a fountain that you can't see coming into the plane. Like imagine like water coming up through a fountain and spreading across a tabletop. That's kind of what I'm thinking about. So there's a net outflow or inflow if you think of it in those terms. And that source is growing. I mean, I have a little bit of flow coming in here and it's pushing these vectors out, but that same source is present throughout the entire flow field, and that's why the vectors keep getting larger and larger. It's like the flow is accumulating. And when we check our divergence, yes, it's uniform everywhere. So the divergence is a kind of a measure of the net inflow or outflow. And for many of these, if you try like this one, for example, well, again, it doesn't seem like flow is coming in or out from anywhere. It's just kind of swirling around. And if we take let's try this one. We take the partial of f1 with respect to x, that's going to be 0. Partial f2 with respect to y, that's going to be 0. And again, I get 0 everywhere. So I encourage you try play around with this, try the different functions, and take a look at the divergence field. The next vector operation to cover is the curl. To compute the curl, take the cross product of the del operator and the vector field, in this case vector f. The result is a vector, and it looks much like the cross product that we had done previously. And to compute this result, expand along the top row exactly as you would a determinant. So I've got this 3 by 3 matrix to help us keep track of the direction. The magnitude of the del operator in each direction is the partial of something with respect to x, y, and z, and our vector f, f1, f2, f3, exactly like we did before with the cross product, except now we're using the del operator here. So in the x direction, if we start with I'd like to use these circles to help illustrate. As we go diagonally down and to the right, we take partial of f3 with respect to y, positive. And down and to the left, we get partial of f2 with respect to z with a negative sign. I'll move these away. Let's do the next one. The j component down and to the right, partial of f1 with respect to z. And then let's start here. Let's go this way, partial of f3 with respect to x. And finally, in the z direction, partial of f2 with respect to x minus partial of f1 with respect to y. So I want to show a quick example of what happens when you take a curl in 2 dimensions. So let's say we've got a vector field that has no z component, um, or changes in the z direction. So any derivatives taken in the z direction are 0. So this del z is 0 and f3 is 0. There's no z component and there's no changes in the z direction. And when that happens, any f3s or partial with respect to z's cancel out. So my first 2 terms are both 0, and the only surviving term is actually the z component of the curl. So in this case, I've got a vector field. It's got f1, f2, and those change across x and y positions. But when I take the curl of that vector field, I'm only going to get a z component. So let's do a quick example. I've got a vector f, depends on x, y. Its components are negative y and x. So f1 is negative y, f2 is x. So let's just look at these 2 terms here. I'm going to take the partial of f2 with respect to x. So here's f2, take the partial with respect to x, it gives us 1. And the partial of f1 with respect to y, it actually gives us negative 1. Yep. And now when we plug those values in, I get 1 minus negative 1, and I get a value of 2. Now, I just wrote this as a single scalar number. Technically, this is a vector. It would be written as 0, 0, 2. But when you're taking a curl in 2 dimensions, you're not going to have an x and y component. So your field only takes a single value. I guess that's a shortcut. Technically, this would be 0, 0, 2. I should mention the curl measures local rotation, and the curl of velocity is called vorticity. Okay, here we are. We're going to feed a vector field in, and we're interested in taking the curl. And let's take a look at our components here, x and y. So if we remember, taking the curl is going to be partial f2 with respect to x and partial f1 with respect to y. So in this case, they're both going to be 0, and sure enough, they are. Let's try the rigid rotation. This is exactly like the example we did on the slides. f2 is x. So partial f2 with respect to x gives us 1 minus partial f1 with respect to y. So minus negative 1 gives us 2 everywhere. Okay. Let's take a look at some other examples. Let's try this shear layer here. So this is tan, the x component is tan h, and it depends on the y position. And there's no y component here. So this would represent a velocity field for a shear layer. And I mentioned before that the curl of the velocity field gives vorticity. So I want to bring up this fluid dynamics concept here, and the curl measures local rotation. So if you kind of think about each point here and whether the flow is rotating at that particular point, that's what the curl is telling you. So in this case, we see the curl is negative down here along the axis, and it kind of drops off. Let's go back to the vector field and take a look at this. Up here, it's like the flow is kind of moving left to right, but there's not a strong rotational component. All the vectors are kind of the same magnitude up here. But down here, I can tell if you placed a little pinwheel in the flow field here, it would be rotated by the flow field. And what's interesting about the curl, or the cross product in general, is you can use the right-hand rule to figure out the sign. So if I kind of take my hand and curl my fingers in the direction of rotation, it's clockwise here, and my thumb would be going into the page, which would give me a negative value. If if the rotation was the other direction, let's put a negative tan h of y here. Okay, now my direction is counterclockwise, and if I curl my fingers in the direction of rotation, my thumb is coming out of the page. So if I check the curl, it's positive. So I encourage you to try the different functions and take a look at the curl operation. Okay, the last vector operation to cover is the Laplacian. To compute the Laplacian, take the dot product of del with the gradient of some function phi. So phi is a scalar field. When we take the gradient of that scalar field, we get a vector. And when we take the divergence of that vector, we recover a scalar. You can go back and watch the previous examples on gradient and divergence. And on your own, you should be able to expand the del operator and the gradient and take the dot product for all of the terms, and you should be able to recover this value here. For shorthand, we usually use del squared times phi. That's an easy way to write Laplacian. The actual result is the sum of the second partial derivatives of the scalar field taken in each direction. So the second partial derivative of phi with respect to x plus the same thing with respect to y and z. Let's work an example briefly. I've got the scalar field phi. It depends on x and y. There's no z dependence. So this second partial with respect to z would be 0. And what I'm going to do is take the second partial derivative of this function with respect to x first. So 2x is the first partial derivative, and then the second partial would just be 2. And then if I take the second partial with respect to y, the x squared drops out. I've got 2y as the first partial, and then 2 is the second partial. So everywhere in the domain, the Laplacian takes a value of 4. Okay, before we go to the interactive tool, I want to introduce this idea that the Laplacian measures how much a point differs from the average of its surroundings. Okay, I have the vector operations tool open, scalar field selected, and the same function that we were just looking at on the slides. And we're looking at the function itself. So this is just our scalar field. And before I click the Laplacian operator here, I just want to think about whether this point is greater than or less than the average of the points around it. Now I can tell by the function that as I move away from 0 in both directions, the value is going to increase no matter which way I go. So on average, yes, the value of the neighboring points is larger. And when we click the Laplacian, sure enough, the value is 4 everywhere. So as you keep working away from the origin, the value of the function keeps getting greater and greater and greater, no matter where you are, and the Laplacian is 4 everywhere. Now what I want to do next is try this sine cosine function, sine x cosine y. And when we click the Laplacian, let's think about what might happen. We've got these peaks and valleys. So in this case, the value is less than its surroundings, right? And in this case, the value over here at this peak, the value is greater than its surroundings. So in other words, the neighboring points are greater. I would expect the Laplacian to be positive over here. In this case, the neighbors are, on average, are less, so I'd expect the Laplacian to be negative. And sure enough, when you click Laplacian, you get the same contours, you just flip the sign. Okay, and in summary, we covered 4 vector operations that use the del operator. gradient, divergence, curl, and Laplacian. You'll sometimes see or hear people refer to gradient as grad and divergence as div. When we took the gradient of a scalar field phi, we ended up with a vector. When we took the divergence of vector field f, we ended up with a scalar. When we take the curl of vector field f, we ended up with a vector. And taking the Laplacian of a scalar field gives you a scalar. And finally, let's remember what each operation measures or tells us. The gradient tells us how steep the function is, and the vector actually points uphill. The divergence measures net inflow or outflow. The curl measures local rotation. And the Laplacian measures how much a point differs from the average of its surroundings. Thank you very much for watching.